Good morning and welcome to Blackhat. This is the second talk of the day. This is the reverse engineering track, and we have Charlie Miller and Noah Johnson here to talk to you about a new project they're working on.
Thanks. So I'm Charlie. This is Noah. Thanks for coming, everybody, and everyone at home. Hi. So today we're going to talk about crash analysis with BitBlaze. Okay, so what are we going to be talking about today? So first, we're going to go back to why is this talk important? So why do I care? And it has to do with fuzzing and the fact that people are starting to realize the hard part about fuzzing isn't actually finding bugs, but actually knowing what to do with all the crashes you find. And then we're going to talk about BitBlaze itself and what it does and how you can use it to help solve this problem. And then we'll move on to a bunch of real-life case studies. So first, I'll look at Adobe Reader and look at how, in general, these techniques can be used with crashes from there. And then we'll look at 4 actual bugs that were found with fuzzing and how you would use that use BitBlaze to analyze those crashes and figure out if they're exploitable, how what the underlying bug is, and that sort of thing. And then finally, we'll try to wrap things up. Okay, so how did I get involved in this? And I should point out, so you probably know me. I work in industry and I'm a consultant and all that stuff. Noah and the rest of the BitBlaze team are actually at Berkeley, so it's sort of an academic and industrial collaboration. So it's sort of, you don't see that too much. And so the question is how'd that get started? So about this time last year, and a lot of researchers go through this, after Blackhat, you've given your talk and then you're like, okay, now what am I going to do? Right, so I started thinking about well, what kind of research do I want to do? This is like last August, and I typically my sort of interests are about finding bugs and that sort of thing, and I'm always kind of thinking about Pwn next March. So I was like, well, what's some things I can use to find bugs that is something I haven't done before? And so basically the only guy I know from academia is David Molnar, who now works at Microsoft Research, but at the time I thought was still in academia somewhere. Anyway, so I called him up and I was like, okay, David, I need you to hook me up with someone who's writing tools in academia that find bugs, and these tools have to work on real binaries. You can't have any sort of restrictions like they have to be small or they have to be written in Lisp or whatever crazy things academics come up with these days. And then it has to work on real binaries. And I don't have source code, I don't have symbols, I don't have anything like that, and I want to be able to find bugs in these real programs. And so he's like, well, it's kind of tough. He gave me the names of a couple people, one of which was Dawn Song at Berkeley, who's here today. So I started talking to her about hey, I want a program that finds bugs, and she told me that, well, they kind of have something that does that, but she explained what BitBlaze was, and I realized that really it solves a different problem than I wanted to solve. So it's not about finding bugs, it's about analyzing crashes. So they actually have something that would be really good at that, and so I was like, well, that would be interesting, let's do that. So that's how I got interested in this, and let's move on to more discussion about why this is a problem and what the problem is. So until maybe a year ago, this wasn't a problem for me because the way that I looked for bugs was I would turn on my fuzzer, it would run for a while, and eventually it would find a bug, and I would turn it off, and I would exploit that bug and give a talk or whatever, right? So I didn't really have a problem with finding too many bugs because I only wanted to find one. But this year, in preparation for Cancer Quest, I wanted to find lots of bugs. And then I saw this problem. And the first person that I know who really talked about this problem was Ben Nagy, who gave a talk about an hour ago. So he's really the king of large-scale fuzzing out in the research world. I'm sure Microsoft does it as well, of course. So in 2009 at Syscan, I met him, and he was giving a talk about some fuzzing he did on Microsoft Word. So, .doc files. And so here's some statistics. So he found 200,000 crashes, and they were sorted into 61 bins, so 61 somewhat unique crashes. And basically, it was him and maybe a couple guys, and that was just too many crashes to analyze by hand. He couldn't do it. So it turned out of those 61, 4 of them were serious security vulnerabilities, and the rest weren't. And the problem was trying to figure out which of these were exploitable, and of the 4, like what was the actual bug. And so just to show that like he couldn't do this himself, he had to actually give these to Microsoft. And I know Ben, and that must have really hurt him to have to do that. So he gave it to Microsoft, and they helped triage them. And the point is, it was too much resources needed to analyze all the crashes. Okay. So then I had this problem as well. So I gave this talk at CanSec West, and in some ways this talk is sort of the continuation of that talk. So at that talk I talked about all the fuzzing runs I did, and I found a ton of bugs, and there were way too many. I couldn't analyze them all. So for example, in preview I found 1,300 different crashes, of which Crash Wrangler says there's really 220 unique ones, of which 60 are exploitable. So there's just no way that I can look at 60 bugs and 60 crashes and try to figure out what the bugs are and if they're really exploitable. This is too much for me to do. Likewise, in Adobe Reader, there were 30 to 40 crashes that I found, and 70 in OpenOffice. So it's like, this is a serious problem. And there's actually a lot of talks at Blackhat this year talking about this. So, I'm not the only researcher who's noticed this. Okay, so more just about this. So the hard part now, I think, which is sort of sad, right? It should be hard to find bugs, but it actually isn't. So the hard part isn't finding the bug. It's sort of prioritizing which of the crashes to look at, figuring out which of the ones are exploitable. For the ones that are exploitable, figuring out what the underlying bug is, so you can either fix it or exploit it, depending on who you are. And then the other thing is, while fuzzing, eventually you can get it so automated that you can just turn it on, walk out of the room, and come back in a month, and there's a bunch of crashes. Trying to figure out how to, what the underlying bugs is. You can't really automate that. You can just make it easier. And so that's sort of the point of this talk is tools to reduce the time from crash to knowing what the bug is, or even further, writing the exploit. All right. So now I'm gonna pass it on to Noah to tell you guys about BitBlaze.
Okay, so I'm Noah. I work with Professor Don Song at Berkeley, and of course I've been collaborating with Charlie over the last few months. So BitBlaze is this binary analysis infrastructure that allows us to effectively analyze binary code. So in this talk, I'll give sort of a high-level overview of the 2 main research focuses of the BitBlaze project. The first is to be able to build a sort of a unified framework that allows us to very effectively analyze binary code and sort of addresses the common needs of security applications while also being easily extendable. And then once we have this platform, the second research focus is to be able to use the platform to enable a wide variety of new security applications. So this picture sort of visualizes what I just talked about. We want a unified platform that we can use to solve a whole bunch of different types of problems, right? So let's look at why this is hard first. Of course, in security applications, we can't avoid having to deal directly with binary code. Oftentimes we want to analyze commercial software that we don't have the source code for, or malicious code, and attackers don't usually release the source code along with their attack, right? So we need to deal directly with binary code, and unfortunately binary code can be very hard to deal with sometimes, as everyone here probably already knows, right? So first of all, binary code is extremely complex, and our analysis system needs to be able to model this complexity accurately if we want the analysis to be correct. So the size of and complexity of modern architecture instruction sets make this modeling very challenging. Another challenge is that binary, of course, is different from source code in that it lacks higher level semantic information. So as a specific example, the function abstraction doesn't really exist at all at the binary level. I mean, we can have call instructions, but I could call any arbitrary address, right? That doesn't tell me anything about where function boundaries are. And so we need to be able to deal with this. Also, lots of times we want to be able to analyze operations within the kernel and interactions between multiple processes. So this requires a whole system view, which poses greater challenges than in just traditional single program analysis. And finally, we need to remember we're trying to analyze malicious code sometimes, and code doesn't always want to be analyzed. So malware commonly employs anti-analysis techniques like code packing, encryption, or self-modifying or dynamically generated code. So based on these challenges, we have a couple sort of high-level design goals which motivate the architecture of the BitBlaze platform. The first is that we want the platform to be able to accurately model the behavior of programs. Okay, so we build precise formal models and then allow tools to sort of accurately reason about the program execution behavior symbolically. We also want to build a core set of utilities that sort of address the common needs of security problems, but can be reused or maybe target different architectures and easily extended. And finally, of course, both static and dynamic analysis have their own strengths and weaknesses. So static analysis is more complete in that we can explore multiple paths, but it's limited by things like indirection and pointer aliasing and a general lack of higher level abstractions. So dynamic analysis is not limited in these same ways, but we can only analyze a single path at a time. So ideally, we'd like to be able to combine both static and dynamic analysis to sort of leverage the relative strengths of both wherever possible. So before I talk about the actual implementation of our system, I want to sort of whet your appetite with some of the cool applications that BitBlaze has enabled. And there's a whole bunch, and I don't have time to talk about all these, but you can refer to the white paper or the website for more information. But the first one I want to talk about is vulnerability detection and analysis. So this is the most recent work, and of course, the bad guys are constantly looking for bugs in benign programs, right? But what about trying to find bugs in malicious code, right? So we're sort of turning the tables, right, and forcing the bad guys to have to write secure code. So using a modified version of our symbolic execution tool, we can sort of explore the execution space of a malware sample in ways we couldn't do before, because typically malware employs things like checksums and decryption routines, which are sort of hard to reason about. So once we've done this sort of symbolic execution and we have these constraints, we split them up and solve just a little piece of them and then use that to rebuild an input that exploits the program. So we've actually found vulnerabilities in 6 different classes of malware samples which could conceivably be exploited by an attacker over the network. So for example, you could take over a botnet or disable a Trojan horse. Of course, this raises ethical considerations, which we won't get into here. But the next thing I want to talk about is model extraction. So we have a static analysis component which allows us to extract models of programs. So suppose we fed this tool a web browser, right, Internet Explorer, and then we extract a model for the function that determines the content type of any given object, right? Once we have this, then we can directly construct an input that causes the web browser to incorrectly infer the type for. And of course, this enables content sniffing cross-site scripting attacks, and we showed that Internet Explorer 7 is vulnerable to such an attack. Another application is protocol reverse engineering. So in security applications, oftentimes we want to understand network protocols or file formats. And traditionally, this is a manual process and is very time consuming, right? But we have this dynamic analysis component of BitBlaze, which allows us to analyze program behavior. So if we give this tool a program that implements a given protocol, then we can watch exactly how it processes messages in that protocol. And how it processes and parses these messages and constructs its own messages gives us a wealth of information about the structure of the messages as well as the semantics. So using that, we can then semi-automatically rebuild the protocol without access to the source code. So hopefully this sort of lets you realize how powerful this approach is. So next I want to talk about how we actually enable these kinds of applications. So BitBlaze is split up into 3 core components. The first component is a static analysis component called Vine, and Vine lets us do static analysis and symbolic execution, and it also provides a set of sort of core utilities for common types of analysis. The dynamic analysis component lets us run a program in an emulated environment and perform very fine-grained binary instrumentation, and also extract semantic information from the operating system as well as the program, and perform dynamic taint analysis. And finally, we have a symbolic execution components. Currently there are 3 of them: Rudder, BitFuzz, and Fuzzball. And these components use the functionalities which are provided by Vine and Temu to enable symbolic exploration. So for a given program execution path, these tools can generate the symbolic predicates that the inputs have to satisfy to follow that path. Right? So in this particular application, the symbolic exploration doesn't play a large role. So I won't describe the implementation of these components, but they play a key role in a lot of our other applications. And again, you can look at the website for more information. So the first thing I'll talk about is this static analysis component, which we call Vine. This is sort of a high-level overview of Vine, and Vine is split up into a platform-specific front end and a platform-independent back end. And then at the core of Vine is this intermediate language, which we've developed to be small, but also flexible in that it can accurately represent the different types of assembly languages that our tools use. So then in this architecture, instructions from a binary program are translated to the intermediate language by the front end, and then all back-end analyses are done on this intermediate language. So this is convenient and allows very powerful analysis because we can write program modules to do various types of analysis without having to deal directly with the complexities of an instruction set like x86, right? This design also allows for really easy extensibility because we can write new analysis systems on top of the existing ones. And so we provide a sort of core set of components we see here. And then we can write new analyses without having to sort of reinvent the wheel and abstract all the low-level details away and focus just on implementing whatever solution we're interested in. So next I'll talk about the dynamic analysis component, again, which is called TEMU. So TEMU is this whole system analysis platform which we've developed as an extension of the open source emulator QEMU. Okay? And so we can run an entire system, including the OS and the program that we want to analyze, within this emulator, and then observe in a very fine-grained manner how the program is running and interacting with the system. So this whole system approach has a couple benefits. First, for a lot of security applications, we need very fine-grained, that is at the instruction level, fine-grained instrumentation on binary code. So because we are the system here and we're the ones who are dynamically converting the emulated code, we can very easily implement instrumentation, right? Another benefit of this is that the whole system view gives us access to the internals of the operating system, so we can track operations in the kernel, and we can also observe interactions between multiple processes. So lots of existing analysis tools only give us a very local view, that is, they use them to analyze just a single user process. But this is sort of not complete, and our tool is more powerful because lots of attacks involve multiple processes, right? And attacks on the kernel, like rootkits, are becoming increasingly popular. So our tool can easily handle analysis of these types of attacks. So we have this system, and we've implemented a couple modules to help with our analysis. The first one I want to talk about is the semantics extractor. So for any given instruction that's executed by the program, we want to know information about, for example, which thread it came from, which process it came from, which module it came from, right? Or oftentimes code is dynamically generated and executed on the heap. So we want to have a mapping between addresses in memory and modules that are used by the system, right? So the semantics extractor is responsible for collecting all this information, and then it passes it back up to the TEMU layer. And the actual implementation of this semantics extractor depends on the operating system we're running. So for Windows, we've developed a kernel driver that registers a couple callbacks to track process creation and memory allocation and that kind of thing. And then again, it passes it back to TEMU through a predefined I/O port. And for Linux, it's a little easier because we have the source code, so we know what the kernel data structures are, and we know the addresses of the relevant symbols, so we can just read this information from the outside, right? The other component that we've developed specifically for TEMU is a taint analysis engine, which we use to perform dynamic taint analysis. And I'll show on the next slide sort of how that works. Finally, we have this interface for TEMU that allows users to very easily extend the functionality and write their own analysis modules, which we call plugins. And so plugins can be loaded and unloaded at runtime to perform whatever analysis the user is interested in. So this whole TEMU system is implemented in Linux, and currently we can use it to execute and analyze code on Windows XP, 2000, and also Linux systems. So taint analysis, or at a high level, taint analysis works by where we taint all the inputs to a program and then track how the taint propagates as the program executes. So I just mentioned we have this plugin interface. The plugins are responsible for introducing taint into the system because where the taint comes from is an application-specific decision, right? So once the data is tainted, then the taint analysis engine monitors all the instructions that operate on that data in order to figure out how to propagate the taint. So it tracks all data movement operations, right? I want to point out this is a data flow-based taint propagation policy rather than a control flow or implicit flow-based one. So we maintain a shadow memory that stores the taint information for every byte of physical memory and bytes on the hard drive. And a benefit of using this is that we can actually track taint through data that's been swapped out or data that's been written to a file and then read back in. Right. And so finally, taint analysis works by checking how the tainted data is actually used by the program. And again, this is application specific, so the plugin determines where to check the taints and which taint syncs to hook. So that's the overall architecture of BitBlaze, but I haven't really talked about how that helps us to analyze crashes, right? I showed you some cool applications, but what do we do? Once we have this system, how do we actually use it to help us understand why a program is crashing? Well, let's look at what we have. We have this whole system emulator, right? And we've written a plugin called TraceCap, which outputs a couple files. The first file is an execution trace file, which is essentially a list of all the instructions that are executed by the program under analysis, as well as the contents of all the registers and memory used by each instruction. And the taint file also the trace file also maintains the taint information for every byte. TraceCap also outputs a state file, which is essentially just a memory dump of the program at the time of the crash. And an allocation trace file, which is a list of all the memory allocations and deallocations used by the program. And it collects that by hooking calls to malloc and free. So once we have these files that give us a whole bunch of information about the behavior of the program that we're analyzing, what do we do with them? Well, we've developed different tools to perform different types of analyses on these files. And I'll go over some of these tools on the next slides that we use for this specific application. So, right, I mentioned trace files contain detailed information about every instruction that was executed by the program. And so we have a whole bunch of instructions, and what do we do with that? Well, the trace files are stored in a binary format. So we have a tool called TraceReader, which parses this file and then outputs it as text. And we can tell TraceReader to disassemble just a specific region of the trace, or maybe even just a specific instruction if we want a more local view. Right? And as part of the output is all the information we could possibly need about every instruction. So, for example, we maintain a sequential index into a trace that uniquely identifies every instruction. We print out the EIP of the instruction as well as the disassembly. In this case, this instruction is operating on memory. So one of the operands that we print out is the address of memory as well as the contents. I also mentioned we have taint information in these traces. So in the case that the instruction is operating on tainted data, we tell you what that tainted data is. So every taint entry is a pair of integers. And the first integer is an ID that tells us the taint source. So where did this taint come from? In this case, we assign ID 1111 to the tainted input files. This means this came from a file, and the byte that was used to taint this particular value came from offset 5 into that file. We also have various process level information, thread IDs, as well as processor level, if, for example, condition flags and the raw bytes. So that's how we actually read trace files. But we haven't done any real analysis yet, right? So lots of times we're interested in just at some particular point in the program, we want to know how this particular byte got set, right? So we have this huge trace, and a lot of times it's not feasible to look through every instruction. So a slice of a program, a variable in a program, is a list of all the instructions that might influence a particular value. So we have a tool, x86 slicer, which computes a data flow-based slice of any variable at any arbitrary location in the trace. And the output looks something like this. So in this case, we're slicing on variable AX. And we can look at this instruction and say, well, the value of AX came from this memory address. Well, how did the value at this memory address get set? Well, the next entry in the slice shows us. We pushed this value at that memory address. Well, where did the value of EDX come from? Again, looking further up in the trace, we can see, oh, well, we moved the value from the stack pointer into EDX. And now we have this sort of very focused view of exactly how the data propagated to get to this final state. And this is a relatively simple example, but hopefully it illustrates the point. So in these applications, we have actually two different trace files. We have one trace file which was collected using an input that caused the program to crash, and then we have another trace file which was collected that didn't cause the program to crash. So oftentimes it's helpful for analysis purposes to be able to establish a correspondence between instructions in the two traces. And to do this, we use a tool called traceAlign. So what traceAlign does is it walks through the traces and computes an index for every instruction. And then alignment comprises essentially matching indexes across the two traces. And then we can print out regions of the trace for which the control flow was identical in the two traces and where the two traces diverged in their execution. So we can see here the traces starting from the beginning up to instruction number 1362 executed identically. And then they branched off somewhere at the disaligned region. So the first instruction in the disaligned region, as well as the last instruction in the aligned region, actually tells us a lot of information. This is why the two traces actually executed differently. So why does this help us? Well, first of all, we have taint information in the trace files, so we can print out, right, this particular branch that caused this divergence, right? We have a divergence because we have a branch for which the target was different in the two traces. Well, in this particular disalignment point, the target of the branch was computed based on a tainted flag. So this means that the original tainted input had some influence on why the programs were executing differently. So instead of just having to analyze an entire trace file, right, we can sort of look in at just a particular location, and oftentimes this tells us a lot of information about why the program is acting like it is. So that's trace alignment. So we have a memory dump and we have a trace file, and I mentioned, right, the trace files have taint information, but a lot of times we want just sort of a snapshot of memory at some location in the trace. Maybe we're not interested in exactly the instruction that operated on the tainted data. We just want to know what data is in this general memory area. So at any location in the trace, we can use the trace file and the state file on a tool called trace dump to actually output the contents of all the memory around any register that's acting as a pointer. So in this case, we can see we're using trace dump on this instruction, and this particular register looks like a pointer, and here's the contents of all the memory surrounding that. And we can see here this particular data is tainted. Okay, so a large class of vulnerabilities are related to dynamically allocated memory. So I mentioned we have this allocation trace file, and we have a tool, allocreator, which basically parses this file, and it can tell us which allocation corresponds to any given address. So here we can see we run it on, well, at the top we run it on address 7260020 hex, and it tells us it found one buffer, right? And so in this tuple here, we see at this instruction count, this is where this particular memory was allocated, and then it was never deallocated in the trace. That's why the N comes from, right? And that was the address and the requested size. We can also, if we're not interested in just a specific address, but rather some location in the trace, we want to know what are all the live buffers at this location in the trace. We can just feed this tool an instruction count, and it will print out all the buffers as well as the addresses. Okay, and finally, because we are actually looking at all the calls to memory allocation routines as well as freeze, we can track when programs are freeing the same memory twice. And so the tool can actually print out what it thinks are double frees. And this could be useful for trying to find new vulnerabilities. Finally, the fact that a byte is tainted at any location in the trace is useful because it tells us that byte is somehow related to the original tainted input. But it doesn't really tell us how it's related, right? So for example, if we taint all the inputs that an attacker has control over, and we have some tainted register at a location in the trace, well, we know the attacker has some degree of control over that, in the value of that register, but how much control? So for this, we have a tool to compute the value set of any variable. So the value set is essentially a set of possible values that any particular variable could take on if the program were supplied different inputs. So this tool works by taking this intermediate language file, which was generated by Vine, and then computing a formula which relates all the inputs to the particular output we're interested in. And then it queries a decision procedure to solve actually this bounds. And in the case that's not feasible to solve exactly, we can solve it to arbitrary precision. So here's an example output. We see for this particular variable, here's the highest and lowest possible values that it could take on, and the influence, that is, how many bits of control does an attacker likely have over this variable. Here is computed 15.9. So these are the tools we use to do trace-based vulnerability analysis. More information about all these tools, as well as some of the other tools we have for operating on traces, is available at our website. And now I'll let Charlie show how we actually use these tools to aid the analyst in analysis.
Thanks. So, so that was basically what. So, you know, I found about BitBlaze, and I knew the problem I wanted to solve, and then I had to figure out, you know. So I should say that basically the two problems I wanted to solve. One was figuring out which of a bunch of crashes are the exploitable ones, and then the second problem was, given one that looks exploitable, find the underlying bug. And so, these are the tools that are available, and we work together, and I would give suggestions, and they would try to implement them. And so I'm going to show you for some real, examples here from fuzzing what happened. Okay, so let's start with Adobe Reader, a favorite target of mine. So I fuzzed it for 3 weeks. This is back in November, and I did 3 million test cases, found crashes at 100 different instruction pointers, of which Bang Exploitable said there were 33 unique crashes. And of those, they categorized them like this. So 4 were exploitable, 8 probably exploitable, 17 unknown, and 4 probably not exploitable. Okay, so there's a bunch of crashes, right? More than I want to look at. I don't even really want to look at all 4 exploitable ones, but I probably would do that. So I mentioned Bang Exploitable, so let's talk about what Bang Exploitable does and what we can do with BitBlaze, which is more powerful. So Bang Exploitable, the way it works is, it doesn't have all this detailed tracing information. So it basically only looks at the basic block where the crash occurs and does a little slice on that. And as far as taint goes, it assumes everything's tainted because it's like, well, it crashed, there must have been a problem. BitBlaze, on the other hand, has full taint information and full trace information. So it can slice beyond the basic block it's in to figure out where data came from, or at least you can have it do that. And furthermore, it knows exactly what's tainted and what isn't. And so from that, you can make more intelligent decisions about what is actually exploitable and what isn't. The drawback, of course, is that Bang Exploitable runs basically instantaneously, and BitBlaze doesn't. So BitBlaze, to record the actual trace, may take several hours. So I think of it as a tool like a fuzzer, where you turn it on, you go to bed, and you wake up in the morning, and you have all your traces. So it may take many hours. And running an actual slice, sometimes it happens really quick, a few seconds, but sometimes it may take an hour or two. So this is something, again, you really can't use sort of interactively a lot of times. You have to run it and then come back to it. But at least you don't have to think about it, right? It's better than reverse engineering in the classical sense. So here's another one about strengths and weaknesses. But the way I use it, so I think about using it as like I use a fuzzer, where fuzzers they find bugs, but just as easily you could just read the binary, right? But the reason I don't do that is it's hard on my brain. But fuzzing is easy. I turn it on and I go away. And BitBlaze is the same way. So it takes longer clock time, but it actually saves you mental energy. Okay, so so it turns out, so the first problem that I wanted to solve was which ones are exploitable. So I have all this taint information, I have these crash dumps with taint, and does that help me actually determine whether they're exploitable or not? The answer to that is sometimes. Maybe, actually not as much as I thought. So I was like, well, if I have taint information and a crash dump, I should basically know what's going on. It turns out crashes, of course, are a little more complicated than you might imagine. So we'll see. One thing it is really good at is eliminating null pointer references. So of those 17 unknowns that Microsoft found, that Bang Exploitable found, you can, with BitBlaze, in just a matter of a minute, throw out 6 of them. So 6 of them for sure are not exploitable. So it does give crash reports with taint information. It's not so good at invalid reads. So why is that? Well, invalid reads, there's nothing exploitable about an invalid read, but what happens is sometimes then if you were to fix things up a little bit, it goes on a little bit and then maybe there's a write or something. But the problem is that's in the future. And you might be able to use Vine or something, but the tracing component at least doesn't tell you about the future. So there's some things it's good at, some things not so good at. Oh, that blue is bright. So this is basically another crash dump and what it looks like. So this is for Adobe Reader, and you can see things like, so it's a read of what was an EAX, which happens to be, I can't really read, 0, right? So this is an example of null pointer reference that Bang Exploitable said was unknown. But if you look at it, it's not, the 0 isn't tainted, so you can kind of, with a little more assurance, say, well, it's probably not exploitable. Here's another one. This is another invalid read on EDX. EDX here is some weird, crazy value, which maybe you think we made it that way. But actually, if you look, I don't see it, but it's not tainted. So it is a weird read, but it's not tainted. So again, probably not going to be exploitable, but I wouldn't say for sure. You can see some other things are tainted, but not EDX. Okay, so that was basically looking at trying to figure out which ones were exploitable. So with taint information and the crash reports, you can draw a little more conclusions, but still it's a lot of crashes, and there's a lot of them you don't really know about. But now moving on to say you do have some crashes you want to look at, and you want to figure out what the underlying causes of these crashes are. BitBlaze actually turns out to be really good at that. So the rest of the talk is basically looking at 4 examples of real crashes from Adobe Reader and other applications, OpenOffice as well, and seeing exactly how you would use the tools to figure out what the underlying problems are, or at least get started. So here's a crash in Adobe Reader. It's still in the most current version, but you'll see that it's not important. So this is a read from ECX, and if you look at ECX, it's 10, so it's near null. So, if I was looking at this, I would probably say, it's probably no point of reference. But I would have sort of a nagging feeling in the back of my head, like, well, maybe it's not, right? So what happens if that 10 came from a wild read, right? And it could have been some other value, and then maybe it writes to that value, and it would have been exploitable, and I would have been really mad if I missed that. Or maybe it was, the 10 or the 0 or wherever came from an uninitialized value, right? So from some buffer that hadn't been initialized. And had I arranged things, I could have controlled that. Or maybe that 10 came from my input, right? I had this big file. Maybe there was a 10 in there, and it used that, and I could have set to anything I wanted. So it's like, I'm pretty sure this thing's not exploitable. My gut tells me it's not, but I still there's this nagging doubt. What BitBlaze can do is it can really quickly get rid of that doubt for you. Okay, so here's using BitBlaze for the first time on live TV. So trace reader, right? So I take my trace. This is the trace of the bad file, the one that crashed. And there's this header option that will tell you, like sort of meta information about it. And one of the things is it'll tell you how many instructions are there. And we're concerned for the crash on the very last instruction. So there's 27,000 instructions. So then I say, okay, now I know how many there are. Now let's just print out what the last instruction is. So I say, I want to see the first one is the last one. So it's the same thing we saw in WinDebug in the last slide. So it crashes on ECX. ECX is 10. ECX is not tainted. So, we already could have gotten that from a crash dump. It makes me feel like, well, at least it didn't come from my input, but it still could have been like an uninitialized variable or a wild read or something like that. So I'd like to know more about where this came from. And, where did it come from? Well, that's what the slicer is for. So let's slice on ECX and see where it came from. Okay, so here's using the slicer tool. This is what the command line looks like. I tell it where I'm at in the program. I'm at the last instruction, and I want to slice on ECX. And then it generates another trace, and then I print out that trace. So let's see what happened. Okay, well, ECX came from EBX, which came from a memory, or came from something plus 10, which was 0 plus 10, and then that got shifted around through various registers, and it started from a XOR of ESI and ESI. So I can know for sure now that the 0 or the 10, I had no control over that. It wasn't from memory. It wasn't a wild read. It wasn't an initialized variable. Just by running one command in BitBlaze, I know for sure this thing isn't exploitable. Where before I was, only kind of sure. So that's one thing that BitBlaze can do really quickly, and it's really good at. So what about comparing what happened in the good and the bad file where it crashed to the good file? So in the this is the same instruction again at the very top of the crash for the bad file. And then I use the alignment that BitBlaze gives you between the good file and the bad file to compare. So there's this script called align.pl. Only Noah writes Perl these days, but that's okay. So you give it the instruction counter where you're in one trace, and then it'll tell you what the corresponding instruction in the other trace is. So it says, oh, okay, for 27,000, you were some other 27,000 in the good file trace. And then I print out that instruction. And so at the same instruction in the good file, I can see that I had a valid value for ECX, which isn't surprising because it didn't crash. But I can see exactly what the value was. And in this way, you can compare the good file and the bad file pretty easily. And you can walk through and see exactly when things go wrong. And then likewise here, what I did was I sliced on that good value. In the good trace, I sliced on the good value. Where did the good value come from, right? Because it didn't happen in the bad file. So if I know where it got set, then I'll know why it didn't get set in the bad file. So this is as a exploit developer guy, I'm done at this point. I already know it's not exploitable. But if I'm a developer, I want to know what happened. Why? I want to fix it. If I care about no pointer references, which hopefully I do, although no one seems to. Here, if you do the slice again, then you'll see, all of a sudden you can trace back the good value, and you can compare the slices from the good and the bad, and you can see exactly where the good value got set in the good trace. So, and then you can compare why that didn't happen in the bad trace. And then so then you could see on the last one exactly the instruction where the good value was set for the good trace, and then you can look at the alignment and see exactly where that occurred, and it occurred in this big unaligned area. So in the good file case on the left, there were 5,300 instructions that were executed. In the bad file case on the right, there were only 6 for that same region, and so that's where things went wrong. So if you would have you shouldn't have went down the branch with the 6 because it didn't set the value correctly. So this is the root cause of the bug here. All right, so then when I flip the button, so then Noah's going to show. So I like the command line interface, but there's actually a GUI version of these tools as well that builds into IDAPRO and can help you. You just have to let it sit for a second. Okay, number 1, yeah. So if you like the GUI and you like IDAPRO, it's pretty cool. You can see the traces in them. So Noah, take it away.
Okay, so, well, this window should be familiar to anyone in the security analysis field, right? This is IDAPRO, and what I've done here is I have a plugin running in the background, and using this plugin, I loaded the trace file, which we collected from Temu, for this particular sample that Charlie was talking about. And the first thing to notice is that the instructions are colored, right? So what do these colors mean? Well, so the blue code was executed in the trace, okay? That's all well and good. And we can go to any particular location in the code, and using the navigation commands, we can walk through the actual execution of the code. Okay, that's nice. We also have a taint list, which tells us all the instructions that operate on tainted data. So in this case, the very beginning of the trace started collecting when the program first read tainted input. So here we can jump directly to this location. It's reading some tainted value. And we have a register window which essentially prints out the contents of all the registers at any particular location in the trace. So here we can see this instruction is operating on memory, and hey, it's tainted because this address that it's operating on is tainted, and in particular the last byte is tainted. And we can see the byte was read here by this instruction. And so we can sort of walk through. Now we see we have a red colored instruction, which basically points out which instructions that we're looking at are tainted. And we continue to walk through. The green means that there's a data dependency. So the instruction operates on some data that was written by this one. And again, we'll navigate through here. So let's go to the point of the crash. We go here, have it all plugged in. So this is the instruction count of the crash, okay? That's great. So now what? Well, so we know the values of all the registers here. What if we want to track actually how these values were set? Well, there's a couple things we could do. We could go to the register window here and we see, well, the value of ECX is read by this instruction. And what I want to do is go to the last time this particular register was written to. Well, now the code jumps to this instruction. It tells us, hey, the value of ECX was written by this particular instruction, right? And so on and so forth. So what if we also wanted, so I showed a slicing tool, right? It'd be nice if we could visualize this in IDAPRO, right? So for any given instruction, we can generate what's called a taint graph. It's shown here. And so for this particular instruction, right, we have the value ECX being written by, let's see if I can make this window bigger so you can see. So we have right, this arrow tells us that, hey, this instruction that we're looking at right above this node, set the value of EBX from C0000 to 0010. And hey, in this slice, back from here, well, how do we actually get this value? Well, ESI was written by this instruction. And so in this way, we can generate a slice of a variable at any particular location. And using these tools is sort of a nice visual way to look at the information that's contained in a trace file, while also enabling all the other powerful analysis features of IDAPRO. So we have a plugin to load a trace file and do this sort of manipulation of data and taint tracking. And we also have a separate plugin that can process 2 trace files and then print information about where the instructions were aligned and disaligned.
Let's hit the button. Yeah, so the GUI thing is pretty cool. I guess Noah's also working on one where you can see the good file and the bad file basically tracing through right next to each other, and then you can figure out where they diverge. Okay, so that was our foray into null pointer divergences. Now let's look at some real crashes. So here's another Adobe Reader crash. This one's fixed in the latest version. So this one, like, you don't need a tool to tell you it's exploitable when you control EIP. But for fun, let's see why that happened. So here's what Windybug says when bang exploitable says it's exploitable. No kidding. Okay, so what's the problem? Again, let's look at the final instruction inside of by using tracereader. So it's a call EDX where EDX is screwed up. But you'll notice that EDX actually is not tainted. So it's like, oh, that's kind of weird. Then you can look in the alignment and see what happened on the good trace. And the good trace, not surprisingly, it called EDX, but it had a good value. So EDX is definitely screwed up, but it's not directly under our control. So let's see what happened. Well, again, the first thing you probably want to think about doing is where did EDX come from? And to do that, you want to slice. So there's the command line you would use to slice for EDX. And the slice comes back, it's only got one thing in it. It says EDX came from this memory address, and the slice stops. So when the slice stops like that, that means one of two things happen. Either it was set before we started tracing. We only start tracing as soon as it basically reads our file. So maybe it was some global variable or something. Or it's some uninitialized value. So it's one of those two things. It's something weird. But one thing we can do is, well, EDX came from a memory address from ESI. So we can see where ESI came from. Okay, so we'll slice from that spot. Where did ESI come from? And so if you look at the bottom there, it was some value, and then you can follow it up the slice here. It was some value. And then you'll notice, oh wait, this one came from a memory address, and that memory address came from, at the very top, from a call. That means a call function, or a call instruction was executed, a return address was pushed on the stack, and that's actually what ends up inside this register. And if you notice, you're like, oh yeah, of course, that makes sense, because look at this value for ESI, and then compare it to what an instruction pointer looks like, and they're like the same. So so this is an instance where that value so it's definitely exploitable. The call EDX is using an uninitialized variable to get that. So if you were to ingeniously set up the stack properly, such that uninitialized variable is something that you would have controlled by doing something on the stack earlier, you would have complete control over the program at that point. So very quickly, and if you've ever tried to reverse engineer just with IDAPRO and a debugger an uninitialized variable, it's really hard to do. So, and this does it really quickly. Okay, so that's one Adobe Reader. So here's an OpenOffice example, just to show this isn't an Adobe Reader only tool. It works on probably any big program. And OpenOffice is really bloated too, so if it can work on that, it can work on anything. And while there is a source code for OpenOffice, I assume there wasn't. I didn't use it anyway. And Adobe Reader, like everyone uses that. No one really uses OpenOffice, right? Well, I know at least one guy does. Dave Vitale always uses OpenOffice. So you can use this to exploit him, and this is a 0-day still, so you can nail him tonight. All right, so let's look at this crash. So you run it, and it crashes inside a memcopy, and if you look, it's bang exploitable says it's exploitable. So it crashes in a write in memcopy. I mean, that's pretty classic. All right, so let's look at the crash a little closer. So again, same lines in BitBlaze I would use. So it crashes. You'll notice that ECX, which is the counter in that instruction, is tainted. So somehow that we've tainted the length of a memcopy. And also you can look at the destination address is tainted, and the source is just whatever. So this looks kind of bad, right? So it's what's worse than a memcopy that crashes in a write? Well, one that for example, that you control the length. All right, so this is just like nothing I probably would have done, but just to show that you can use this tool and that it can be done automatically and very quickly. So you could have just run val set analysis on all those tainted things I just talked about, so the length and the destination. And so here's an example of running it on the destination address. So we already know we can, there's taint in the destination address is tainted, but exactly how much control do I have? Can I move it 1 bit, or can I just set it to arbitrary values, or what? And so if you see this, you run it, so it works out to be 16. So approximately 2 bytes of the destination address we have control over. So it's sort of an interesting use of the tool, and there's exactly how you would run it. And there's more in the white paper. So there's more examples There's another OpenOffice 0 day in the white paper, and then the white paper is like 70 pages. So download it. I have the link at the end of the slide. So check it out. It has a lot of tool usage. Okay, so now let's see what exactly happened. What's the underlying bug here? So in order to see what happened, we want to go back in the trace, right? So we know where it ends, but what happened before that? And what I've done here is I've printed out what happened till the end, and then I just grepped out all the stuff that was in the Windows libraries, because I don't want to care about what happened inside of memcopy. I want to care who called memcopy. And that's what I get. So I get this. I can see the call to memcopy, the 3 pushes from memcopy, and then I can even look up ahead and see how things were calculated a little bit. Okay, so in this case, the memcopy looks something like that: 2 addresses and a big length, which we know is somehow tainted. Okay, great. So let's see where the source of this memcopy came from, and then I'm going to use Alloc Reader to figure that out. So I plug in the address into Alloc Reader, and it tells me, okay, it was the source was here, the size was this, so I know how big the buffer was allocated for the source, and it happens to actually be the same size as the length of the copy. So the memcopy is, in source code was probably like destination source, string length of source or something, I don't know. And then I can see where it was. I can look and see exactly where in the instruction trace it was allocated. Okay, what about the destination? Well, I can do the same thing. I use Alloc Reader, plug in the destination address, except this time it comes back with something a little different. It says, yeah, this address you're giving me, that wasn't inside of an allocated buffer. It was close to this other allocated buffer, though. And so it turns out, if you look, we're actually starting to write already past the end of a buffer that they intended us to write in this bug. All right, so let's see, like, where the heck, what went wrong? What's up with this destination address? So if you look in the trace I already had on the screen, it says exactly how this was calculated. It was calculated as EAX plus 8 times EBX. EAX happens to be the exact thing that we saw in Alloc Reader as far as where it was, the destination buffer was allocated. And EBX is this like very large number, right? FFA8. So that's probably too big. Right? So either the size of the allocation was too small or the offset was too big. One of those 2 things went wrong. So let's see, let's look and see which of those 2 it was, if either. So the allocation size, let's check that out. So we can see where that came from. So it was pushed there. It came from AX, which was FF6C times 8. Okay, so whatever AX was, we multiplied by 8, and that's the size of the allocation. And again, we knew where this allocation occurred, which sometimes that's hard to figure out, thanks to Alloc Reader. Okay, so then we slice on AX. So again, we just run the slicer, and we see that, okay, it came from these 2 like fairly large words added together, right? And it became, so it was like, it became 1 FF6C. And then it got moved as a word into EDX. And so then what happened was, instead of being 1 FF6C, it became just FF6C. So there was an integer overflow of the short variety here. And so the allocation was too small. And we were able to figure that out pretty quickly here, just using BitBlaze. So you're probably done at that point, but just to be sure, let's check out where that offset came from. So we know the allocation was probably too small because there was an integer overflow. But let's see anyway. So the way you do that is the same thing. We'll just do a slice. And you'll see, you can trace it back, and it's like, oh, look, this is the same value as we saw in the last slice. So what happened was, there were 2 values. They wanted to add them together, make a buffer that size, and then they wanted to write to like sort of the middle part of the buffer. And so what happened was, the allocation was too small, so when they go to write to the middle, it's actually past the end. And that's the bug. So again, we were able to figure that out pretty quickly without having to use IDAPRO or debugger too much. Okay, so if anyone follows me on Twitter, you would have seen one night. I wanted to sort of see how this really works in real life, right? I say it's easier, I say it's quicker, but the real test is like, is it, right? So there was this vulnerability in Adobe Reader rated as unknown by being exploitable, but it looked pretty good to me. So I had a volunteer who works at IC with me to take on the role of the regular security researcher while I was going to use BitBlaze. Okay, so here's the matchup. It's me, who I call myself Bitmaster, because I use BitBlaze, right? Versus Dion. So you might know Dion. He's a top-notch security researcher. Dion let me cheat. Blazakis, right? That's how you say his name. So anyway, he's sort of famous for having the JIT spray in Adobe and the pointer inference. So anyway, so it was me versus him, and he could use any tool he wanted except BitBlaze, and I could only use BitBlaze. So let's see what happens. Okay, so here's the crash. This is an Adobe Reader. This is still current, so this is your first 0 day of Blackhat probably. So 0 day in Adobe Reader right here. Take a picture with your camera. So the reason that bang exploitable says it's unknown is because it actually crashes on a read. ECX is invalid. But then just a few instructions later, it's a write. So there's some promise that it's going to be good. And so again, bang exploitable says it's unknown. If you compare the good file and the bad file, there's just some byte and a big old, in the big file. C1 is for the good file, CF is for the bad file. So that was it. I said, okay, Dion, go. So and then I went. So what I did as the bitmaster was I tainted this bad byte, and I got a bunch of traces, and I started doing slices and that sort of stuff. Dion, he got IDAPRO up, and he started running his debugger, and that's where we start. All right, so let's see what happens. So the first thing I do is the same thing I've done every time in these demos, right? I see where it crashes. I can see that ECX is not tainted, okay? I can slice on ECX, and I can see ECX actually came from adding two heap pointers together. So usually you don't add heap pointers together. It doesn't really, not a good thing to do. And when you do, things crash. And so I already found out just by doing one slice what the sort of underlying problem was. And another point is this address that's twice a heap pointer is actually reachable by heap spray. So this is something we can actually probably exploit. So yay, 1 point for bitmaster. Okay, poor Dion has no points. Okay, so then the next thing is like, okay, that sort of gives me an idea what went wrong. Now, what's up with the CF and the C1? Why was that important? So then what I do is I figure out, okay, well the crash was in cool type. So let's see the first time a tainted instruction was used in cool type. See if I can figure out what went wrong. So the first two are irrelevant because it's writes on top of tainted data. So the first time a tainted byte was used was this E4 was read. So it's like E4, huh, that's interesting. Like that's not C1 or CF. I wonder where that came from. So you can do the alignment trick and see what it was in the good case. And in the good case, instead of E4, it was D4. And you'll notice that this E4 and the D4 are both tainted, as you would expect. Okay, so it's like, huh, well, where did that come from? And so to see where the E4 came from, you need to trace back before it got into the crashing DLL cool type. So if you just look at a few instructions before that, you'll see it came from a big copy. So it looks like it was inside memcopy or something. And you'll see it came from a buffer with like E4, 9B00, and so forth. So we can use the state reader to just grab memory near there. So if you do that, you'll grab a bunch of memory. There's my E4 that's there. And you see things like loca, max, p, name. If you just do a Google on that, you'll see that this is a true type font. And then you can use state reader also to say, are there any other bytes nearby tainted? Nope, E4 is the only tainted byte, it tells me. So I know that this is probably whatever I had before in the PDF. It was compressed, it got decompressed into this, and that one byte that was tainted before got changed into an E4 in the decompressed stream. Well, that's pretty cool. So I'm going to win, right? No, actually, not this time. So Dion, meanwhile, sitting in the ISC headquarters, he decompressed the good font. And then he examined the decompressed font. So okay, he has the decompressed font. And then he looked in the crashed file in the heap to see where he could find something that looked similar to the decompressed font. And he found a spot in memory that looked exactly like the decompressed font, except guess what? It was different in one byte. He saw that it was instead of a E4, there was a D4. So he was able to pull that out from the debugger to get what the decompressed bad font was, because you can't actually just decompress the bad PDF because it's corrupted. So anyway, so he was able to like really quickly, just by searching memory and being smart, figure out what the decompressed font was. So he gets a point for that. Well done, Dion. Okay, so round 3, Dion continues while I'm still like slicing and stuff. So he starts reading the TrueType font specification, which is something I would avoid if you could. So he realizes, he's like, well, what's this E4 thing, right? I'm going to figure out in the spec what it corresponds to. And what it corresponds to is an offset, to where you can find this max P guy. So in the good file it's E4, and the bad file is D4. So they're looking at different spots. So you end up using a different max P table. And the main difference that is sort of the real underlying problem is that for in the good file there's this FFFF there in this table, but it corresponds to max size of instructions. Because everything is shifted now. In the bad file, instead of that, the FFFF becomes max component points, and it turns out that's bad. So what Dion does next is he creates a new PDF that's not compressed, so it has an uncompressed font, and then he manually makes max component points FFFF. And what he finds is then Adobe Reader still crashes in the exact same way, but now we have a very small PDF, it's uncompressed, and we know exactly what's wrong. So it's the same crash, but now it's easier to analyze. He's starting to kick my ass, so we need to start improving, or else you'll be like, well, I'm just going to hire Dion. I'm not going to even use BitBlaze. So now I go back to BitBlaze. So I had the simpler PDF now. So now I take the simpler PDF that's uncompressed, and I now taint the FFFF, and I see what happens. So instead of tainting the CF from the compressed font, I'm rerunning everything with the FFFF tainted to see what happens. Okay. So I do the same exact thing again. I say, okay, tell me what instructions were dealt with tainted data, and they were inside of the cool type DLL. That's what that grub is for. And right off the bat, the very first lines, it starts to tell me how this FFFF gets used. So first it reads the 6th byte of offset, reads that into DH, and then the 7th byte. So it's reading it's reading both of those FFs, so they're both important. And then what's it do? So now they're in DX. And then down there, it adds 8 to it. Okay, that's fine. So it's FFFF plus 8. So it's 1007. And it pushes that to some function. But then what does the function do? Oh no, it thinks that it's a word, and it copies it into ESI. And so instead of being 1007, it's now just 7. That's an integer overflow. So, and I was able to find that real quick. So 2 to 2, it's a tie. Right, that's the nice way to always end a talk. So then what's the end of the story? And this is all outlined in the actual white paper, but I don't have time here. So this FFFF we saw had 8 added to it. It overflowed, and then it uses this for an allocation size. So it multiplies by 4 to get the size because it's like D words. So the size in the bad file is 1C. It's way too small. 11 buffers are allocated to this size, and then routines start operating on these buffers. They think the buffers are really big, like 40,000 bytes big, but really they're like 30 bytes big or something. I don't know. And so they all smash on each other, and then you get crashes and stuff. So that's the bug, and we were able, that's the competition. But then it was like, I said it's a nice way to end talks, but I'm not really that kind of person. So I want to have a winner, right? I'm an American. We can't have ties. So the next thing was Dion. He actually goes, and so BitBlaze can't do this. So he actually writes. He does the heap spray. He gets everything running, and so you can't argue with that. Dion is the winner this time, but still, BitBlaze did good. Okay, so got a couple minutes to finish up here. Let's talk about it a little bit. So BitBlaze did pretty awesome on these things. It's still not going to replace Dion at this point, but hopefully it sped up the process. And there's some things that BitBlaze did that if we wouldn't, we were still sort of working together, that if I wouldn't have shown him, oh, this is where this came from or that where it came from, it would have taken him a lot longer. Okay, so the trade-offs. BitBlaze, I already said this, it's not fast. So it's something you have to basically run overnight to get the traces. There's also some things it can't do because it runs out of memory. So if you want to do full taint runs for those crash reports with taint, sometimes you'll run into problems. The traces are sometimes many gigabytes, so you got to have a big hard drive ready to go. And again, the bottom line I think is that it might not be faster. Like if you said, Charlie Miller, you need to find exploit for this bug in the next 2 hours. BitBlaze probably wouldn't be the tool for me because in clock time it's not really faster. But if it's like, okay, you have a week to do it, and you have 10 of them to do, well, then it's probably a good choice because it's going to be able to, I can run it overnight, and then it'll help me while I'm actually thinking about it go faster. Okay, so conclusions. BitBlaze is a general tool that can do lots of things. In particular, it can do this crash analysis. Crash analysis is tough, and even with taint information, there's a lot of times you don't know what to make of crashes. But it is something that will hopefully speed up your reverse engineering. The white paper, like I said, it's like 70 pages. It's full of gory detail. Check it out. Code's available too. This is the BitBlaze team. So they were great. They did a great job. Their tool works. And so here's links to the code where you can get BitBlaze and play with it yourself. Also links to the slides from today and the white paper. So please check it out. And that's it. So I don't know if we have like 3 minutes for questions. If anyone has any questions, we'd be happy to take them. Yeah, back here. Yep.
So it looks like I can fully automate the tracing and the tainting, but not the.
So this is a guy who had his picture in the slide, so he thinks he can ask a question. It's Ben, right? I can't really see, but I think so. I recognize his accent. So he's the guy who finds like 200,000 crashes in a work. Okay, what's your question?
So it looks like I can automate the trace dump and the tainting because I can just give that and automatically taint it, but not the subsequent analysis. Is that right?
So he was asking what can be automated and what can't. So you can certainly automate the trace taking. You can automate the crash dumps that have taint information, and then you could write little heuristics on top of that. You can automate like some val set stuff. So like if you notice things are tainted at the crash site, you can ask how much control you have over those things. But like knowing you could automate a slice, but it wouldn't really do you any good probably because it sort of takes a human to interpret that. So yeah, there's a lot of things you can do, but then the sort of figuring out the bug part, still it's going to take a human to look at that. Yeah, back in there.
Maybe I'm.
No Windows 7. How come? And how hard to bring that on stream?
All right. So the question is, how hard is it to support Windows 7? Noah.
Right, so for the Windows platforms, of course, we don't have the source code, and for getting this operating system level semantic information, we need to sort of get deep into the internals of the system. So it involves sort of manually reverse engineering the kernel, and we just don't have the bandwidth right now, but that's sort of the next step. So
it's not a QEMU-based limitation from the old code base you're using.
correct. So it's just so QEMU might support Windows 7, but we need additional information not provided by QEMU. That's where the TMU extension comes in. And so it's not that it's not possible to do, it's just that we haven't done that yet. And we have no need because all the samples can run fine in 2000 and XP. Right? But it's on our to-do list.
Thank you.
Is BitBlaze free? I didn't see it. I came in late, so is it free and open, or is this an enterprise product?
BitBlaze is free, first of all. The core components of BitBlaze are open source, and you can find those at our website. We've also released binary-only versions of some of the tools that we've shown in this presentation, and you can get the distribution from that at this link.
So it's all free, some open source, some still closed source, is that right?
Correct. Yeah. Most of it is open source. There's just a few tools that we haven't yet released publicly.
Any other questions? Oh, yeah.
The trace file you had for every single process, right? The whole OS and subsets.
The trace files we were looking at were for just a single process, but the trace collection utilities can output traces for every process.
Okay, so thanks.
All right, so you get a trace for the process that crashed or whatever, and then you can actually also just find out the instructions from that trace. Even finer are only the ones that deal with tainted data. You can ask it that too. But yeah, you don't have to worry about all the processes. That's one of the things that it does for you. Other questions? I think we're out of time anyway, so thanks everybody.